Hello, my name is Sahana Nagaraj. Today I'm presenting my MSc research project titled Biometric Security, Securing a Facial Recognition System Against Deepfakes and Spoofing Attacks. So, the deepfakes are the AI-generated synthetic media that digitally replace a person's face features with another's. So, creating a highly realistic but fabricated content has a facial recognition systems become widely deployed in security applications, banking, and the identity verifications. So, this sophisticated deepfake presents a significant vulnerabilities to biometric authentication systems. My research addresses the critical challenge by developing an AI-powered detection system. And the research question and the objectives are the problem which we are facing is that deepfakes generated by advanced algorithms like GNAs and the diffusion models can now bypass our traditional security measures. These synthetic faces are so realistic that even human observers struggle to distinguish between them. My research question is how can we effectively detect the deepfake images using a transfer learning with an advanced CNN architectures, particularly DenseNet 1-to-1, and what factors contribute to optimal detection performance? This is crucial for the maintaining the integrity of biometric systems and the literature review shows three key trends. Firstly, the field evolved from the traditional forensic to deep learning approaches as GNAs became more sophisticated. Secondly, CNN architectures like a DenseNet consistently overperform like a traditional methods with a transfer learning, proving highly effective. Then at last, while approaches like a temporal analysis shows promise significant gaps remain in the cross dataset with generalization and a robustness. So the proposed framework shows a biometric input, the data preprocessing and the augmentations with the CNN-based liveness detections and the multimodal biometric detections. Um In the methodology overview for this research, I have used the comprehensive of 140K real and the fake faces dataset, which contains 70,000 authentic images and 70,000 of deepfake images, which are generated using various techniques, including a style GAN and progressive GNAs. So I implemented and compared the three state of architecture like CNN architectures, that is a TensorNet and ResNet 50 and FNet BO. So all these models used transfer learning with the image ImageNet pre-trained weights to leverage a rich feature representation. My methodology, including a comprehensive data augmentations with a geometric transformations and a photometric adjustments, um, mm, and the comprehensive simulations, noise injections to the enhance model robustness against the real world variations. So the code implementations gives the model architecture, the binary classifications has the DenseNet primary and the MobiNet, which is a lightweight alternative for the real and fake detections. We have used the custom layers for the global average pooling 2D and the fine tuning. The data preprocessing is with the rotation and there are normalizations of the pictures and the data sets and in the data preprocessing I have to like the comparisons of 70,000 versus fake versus a real pictures and um, we have normalized the pixel values to the range of 0 and 1. Um, the evaluation plans also has the fake acceptance rate and the percentage of unauthorized users incorrectly accepted. The FRA and FRR is the fake rejection rate, which also gives the percentage of authorized users which are incorrectly rejected. And I focused on the DenseNet one-to-one as my primary architecture because of its unique dense connectivity pattern. Unlike traditional CNS, every layer in the DenseNet receives an input from all previous layers, enabling an efficient features. So to reuse and solving the vanishing problem, and um, the architecture is particularly effective for the deepfake detection because it can capture both low-level texture details and the high-level of cinematic information, making it excellent at detecting the subtle manipulation artifacts that characterize the deepfake. This one in the framework comprehensive. So the scalable architecture has a dual model approach with a lightweight mobinet for the mobile or the IoT devices, and uh, in the result and comparisons. The experiment results clearly demonstrate the DenseNet one-to-one superior performance. My DenseNet model have achieved like almost 94.2% of the accuracy. I have got an accuracy of 92.4%, and the model shows for excellent balance with 93.8 percentage, and which indicating strong performance in both detecting defects and the preserving authentic content. So the ROC score is 0.98. Mm, and uh, which demonstrates the exceptional discriminative ability. Importantly, the interference time, just like 15.3 milliseconds per image, makes the system suitable for the real-time applications, which is crucial for the practical biometric security implementations nowadays. And the key findings and impact. My ablation studies revealed the several key sites which transfers learning with a selective fine tuning, improved accuracy by 15.8% compared to the training from scratch. So the data augmentation strategy contributed an additional of 6.9% accuracy. This research demonstrates that the DenseNet can effectively balance detection accuracy with computational efficiency, making it highly suitable for the real world deployment in a biometric security. And in conclusion, I would tell that while achieving the 94.2% accuracy represents a significant progress, I acknowledge the limitation, including the dataset simplicity and the need for enhancing adversarial robustness. For the future research directions, including an integrated temporal dynamics for the video analysis, exploring the multi-model approaches, combining the visual and the audio features, and investigating the transformer based on the hybrid architectures. So, in conclusion, this results provides a foundation for the deepfake detection in biometric system. The DenseNet-based approach offers an effective solutions for the securing facial. The goal of the project is to identify whether the given video frame is real or manipulative. Now I have demonstrated my deepfake detection system results. I have my code which was already executed in the Visual Studio with all the outputs ready to show you the model's performance in action. And I have started by loading the datasets of the real and fake face images, applying the pre-processing steps like resizing, normalization, and the data augmentations to improve the model robustness. Here you can see the TensorNet model implementations. Let me scroll to show you the model architecture, and training setup. Um, For the model, I use a DenseNet, a convolutional neural network known for its dense connectivity between the layers. This helps in better feature reuse, reduces the number of parameters, and improves the gradient flow. As you can see here, I have implemented the DenseNet one-to-one with a transfer learning from ImageNet. The model was trained on 98,000 images and validated on 21,000 images within comprehensive data augmentations. And I fine-tuned a pre-trained TensorNet model on my datasets using a categorical cross entropy as the loss function and the Adam optimizer for the training. Let me show you the training and the performance results for the confusion matrix. So after training the model, I have achieved the highest accuracy in detecting the deepfakes. So here is the confusion matrix and the highest accuracy results which I have achieved. So you can see, um, yeah, here is the confusion matrix, the classification reports where I have got like accuracy of 94, like almost 95 percentage, and the confusion matrix shows an excellent performance with the low false and low false positive rates of only 6.2%, meaningly it perceives an authentic content very well while effectively detecting the deepfakes. And the result demonstrate that a DenseNet can effectively capture a subtle face and consistencies introduced by the manipulation. Now let me demonstrate the actual prediction on test images. You can see the predictions of the real and the fake images. Here you can look at the probability scores, like I have got like 0.12 and 0.8 or 0.9%. It's very close to zero, so correctly classifying this as an authentic images with a high confidence. See the test accuracy is 0.97, test loss is 0.907, and the AUC score is 0.99. Um, like the deepfake images predictions are very close to one, so successfully identifying this as in synthetic images. Notice how consistent the model is in its predictions. The system detects subtle manipulation artifacts that are invisible to human observers. Um, uh, here the precision, here actually you can see the detailed output and performance matrix which I got. The accuracy, the precision is almost 96 percentage, and the accuracy is 97.5 percentage, and the F1 score is 97 percentage. The even the recall precision is 99 percentage. Mostly importantly, for the real world applications, the interference time averages 15.3 milliseconds per image, so making this subtle for the real time deployment. Um, and let me quickly highlight the key achievements visible in this result. You can see that ANSNet 121 significantly outperformed both ResNet 50 and the EfficientNet view. The model successfully balances the accuracy with the computational efficiency. The ROC, the EO ROC is very less, like I got see the AUROC is 0.99 percentage, and the exceptional demonstrates the ability between the real and the fake images. So in future I plan to extend this to a video level analysis and integrate it into a real time detection systems for enhancing the biometric security applications. Thank you.